So this is the front cover of the exam. Now I'm showing you guys this because I want the first thing you need to do when you get into the exam, when you're allowed to start writing, is you should make sure that you put your name on the page. If you forget your name on the page, then I cannot mark it. This is probably, and the thing is that I may not be in the room, so I may not know who's got what exam. So please put your name on there. Now, next, we're going to look at what else is here. So we're going to go to this part here. The exam is broken up into 95 minutes. That 95 minutes, oopsies, oh, come on, don't screw them now. It's a bit confusing because it's, no, I'm not showing you the questions, Brendan, nice try. I'm kind of concerned that I'm accidentally gonna push the down button too far, and then some of you guys that have got screen capture are gonna be like, oh, if you go back to, you know, exactly frame 13, you can actually see like question 1 of the multiple choice. Because I know some of you guys are nerds like that. No, I'm not doing it. All right, so grab a look. So firstly, it's an 85, we've got 85 minutes of writing time, 10 minutes of reading time. Now, as I always say to students, use this wisely. Some students I just see rock up and they go, oh, cool, I guess that I'll just sit here and wait for the exam. No, you've got 10 minutes to read, to use your time wisely. What that means is plan. What are you going to start with? What will you end? What are you going to skip? What do you think is going to take a lot of time? Because you don't want to look at a question and be like, wow, that question is going to take me like 20 minutes to do. Then skip it. Leave it till the end. Do the easy marks first. My example that I always tell students is do the easy marks first. Because if you do the easy marks first, then that means, one, it does two things. One, you build your confidence. You're like, hey, I've got this. And you might think, yeah, so what? That doesn't matter. It's like building your confidence in an exam will make you faster and it'll make you more accurate because you'll be like, okay, I can do this. If you're going and trying to do these hard questions, and you're like, oh my God, I can't do this question. I can't do this question. I can't do this question. Then you're going to be like self-defeating. You're going to give up sooner. It's all about psychology. So build up your confidence is a good for psychology. The first one, the other reason as well, is it gets marks in the bank. Marks in the bank. If you run out of time and you've wasted all your time doing hard questions, you don't get as many marks in the bank. Whereas if you just do, hey, cool, we've got a question here, it's like 1 mark. And it's like, you know, it's a 1 mark question and it says, you know, what are the 3 colors of the wires that go into an electrical outlet? Well, I know that. Blue, brown, and green, or green and yellow. It's like, done. There you go. There's 1 mark. Rather than spending 20 minutes looking at a question like, it's like, okay, you have 1,000 joules worth of energy heating up a block of ice that is currently at -20°C. And you're like, you spend 20 minutes to just get 1 mark there when you can get a 1 mark answer really, really quick. So yeah, use your time to evaluate the questions. Plan where you're going to start. You know, you might want to start at the multiple choice. You may want to leave the multiple choice for later on because you may want to do some of the short answer. As go in there with a strategy. My strategy was actually completely different to that strategy that I just told you. My one was always like, I did the easy short answer first. Then I did the multiple choice, and then I did the hard short answer. I always tried to leave the multiple choice till later on because I thought worst case scenario, I can just guess them. That was my answer. But that's sort of the way that I did my exams. You might want to go from front to back because multiple choice is usually pretty easy to do, gives you guys a boost. But you might think that you just came out of doing areas of matter, so hey, that might be an easy one for you to start with, right, and leave this one to the end, even though this is the second on the list. Whatever your choice is, but just don't go in there with a plan. Plan. That's what I'm trying to say here. Now, let's grab a look at the next part. Have you marked the electronics test? Is someone asking? No, I have not marked the electronics test. I'm working on it. I've still got it here. I was up till 1 a.m. marking the year 10 test because they're getting more grumpy at me than you guys are, but it's on my list of things to do. I'm probably going to start marking it this afternoon because I want to try and have it done so that if then maybe then I could even offer, hey, if you want to come after school and grab a look at your electronics test, then we can actually go through it together or something like that. I don't know. Now let's look at the actual breakdown. So you can see that it's out of 80 marks. You can see that there are 20 marks in multiple choice. And then you've also got 20 marks in thermo. Have I got this right? Oopsies, I put a typo on this. I put a typo on the goddamn exam. Whoops. Oh, well, it doesn't matter too much. I say it doesn't matter too much because out of all the things that could make a difference, this is probably the one that's like, there are 20 marks. I'll tell you the truth though. There are 20 marks in the electricity section, and there are 10 marks in the origin of matter and 10 in the experimental design. These multiple choice are split between here, here, and here, which I think is like, I think it's like 7, 7, 6. I think that's how they're split. The experimental design, well, that will involve, that's again this idea that you know the independent variables, dependent variables, you know about the aim and the safety and all that thing. You should also know how to deal with errors, so percentage errors, adding and subtracting, and also how to graph errors. So just be aware that may be on the exam, some of these things. That will be in the experimental design section. So just be aware that there are 7 marks. So there are 10 marks, there are 7 questions. So that's what they will relate to. These marks are based off this experiment is based off one of these topics. So there may be some extra questions about one of those topics as well. But that's what they are. And the reason I'm giving you guys these types of questions because these show up in year 12. In year 12, there's actually a whole big experimental design section where you have to sometimes they'll give you a prompt and they ask you to make an aim or they ask you to make a hypothesis. Sometimes there is a bunch of data and they ask you to make a graph and then to discuss the graph. Is it linear or not linear? Not ohmic, obviously, because ohmic doesn't mean linear. Is it is it positively? Is it going up? Is it a positive increase or a negative trend? You might have to draw in percentage errors. As I said, I'm just going to leave it all, possibilities are out there. I'm not going to tell you exactly what's on there because obviously it's an exam. I'm just going to tell you, hey, heads up. No, yes, ohmic graphs are linear, but not all linear graphs are ohmic. This is what we discussed yesterday, because I had a bunch of students that had a graph that looked like this. 1B, 2B, 3B, and then they had their resistance, and then they had this, and they said, oh, this is ohmic. And I said, no, this is not ohmic. This is linear, but it's not ohmic. What would an ohmic graph look like? An ohmic graph only works if your axes are voltage and current. That's the only time that you will get an ohmic looking graph. ohmic does not mean linear. So many people just was like, oh yeah, it's ohmic. It's like, no, it's not. Yeah, cool. Hopefully you understand that. So that's out of 80 marks in total, ignoring this typo. Actually, can I fix this typo here? I should be able to. Ah. Can I fix it? It won't let me fix it. I don't know what I've done. I've done something. Ah, here we go. So, and the rules are also underneath that. We can see the rules here. Students are permitted to bring into the exam room pens, pencils, highlighters, erasers, 2 pages, 1 A4 sheets of pre-written type or typed. You can have either or, and 1 scientific calculator. 2 pages, 1 A4 sheet, 2 pages, 1 A4 sheet, comma, double-sided. I should say that actually, just in case people get notes. Students are not permitted to bring into the exam blank sheets of paper or whiteout tape. So you can't bring in like working out paper. You're supposed to use the exam for working out paper. Unless otherwise indicated, the diagrams in this book are not drawn to scale. And then, yeah, so then we've got, there are 16 pages and a full formula sheet. Students are not permitted to bring into the exam room mobile phones or any other or unauthorized electronic devices. Yes, yeah, that's otherwise in the case Joe scale. Crying is allowed. Please do so quietly. It can be very disruptive. Do not wipe tears on exam paper or any other bodily fluids, preferably, but you know, whatever. I had to mark an exam once at a student. Oh my God, worst exam. I had to mark an exam once at a student who had a blood nose during the exam. There was blood all over the exam. I was like, Jesus, like, this is like a biohazard at this point. I used to work, I did a small stint working for the VCAA, and I used to get all the year 12 exams. So yeah, some student, and they kept going. They kept doing the exam. This is the formula sheet. I've already given one of these out to you guys. So the formula sheet has all the formulas you can use for thermodynamics. We've got some latent heats down the bottom, the specific heats. We've got all the formulas used in electricity, at least all the ones that I could think of. Even got AC period. I don't know why there's a gap here. Why is there a gap here? I think I may have removed one of these questions, one of these because it was wrong. I don't remember. I don't know why there's a gap. I'm going to delete this gap. Okay. And then last but not least, we've also got the matter stuff. There's only 2 formulas. Don't worry about this formula, guys. If you guys see that formula, like, oh my God, we never studied it. Don't worry about it. I'm not going to give you a question on it. Same with this stuff here. I'm just putting them on here for future. So when I do eventually get time to teach like the units of measurement, I didn't screw this up. That should say meters at the end there. Oh my God. Sorry, guys. I'm just a reminder to you guys, I'm the only year 11 physics teacher. So whenever there's a mistake, like I'm the only one, I have to pick up my own mistakes. Usually what we have is you have a team of teachers that go, yeah. And then you also have a periodic table. You may need to use this periodic table because if you go, hey, I've got some, where is it, uranium, and it loses like, we've got some thorium, undergoes beta decay, it's going to go up to palladium. So you might need to know what the symbol is for 91. So that's the formula sheets. Are there any questions so far? Any queries about what's going on with the exam, so on and so forth? Okay. Next. Here. Ladies and gents, I have started to upload the videos. So if you have a look down here, you guys can actually see that I've uploaded the lesson from Tuesday and the lesson from Wednesday. Now, some students were asking me, they said, sir, can you, hey guys, I've got a couple of quick. I had some students ask me some questions about year 11 physics, specifically beta decay. And so I actually made a quick 10-minute video about just beta decay. So if you're someone that's like, whoa, I've got confused between the difference between beta plus and beta minus, there is a whole video for you. Speaking of whole videos though, you guys can actually go here. You can go to this is Matthew Greer, this is me, this is the same thing. If you guys go to playlists and you go to, if you guys go to playlist and you go to year 11 physics, you can actually see every single video that I put up last year. So we've got all these ones on, you've got one, this is actually the one that we did at the start of the year, by the way. So this is with you guys. Because remember that when we were locked down for that one period, that one little bit, well, you guys can actually access every single video that I uploaded last year, plus that one, which I uploaded this year. Now, it doesn't have all of them, obviously, because their lockdowns are at different times. So we've got physics, we've got charge, we've got moving charge, we've got electricity, we've got Ohm's law, we've got Kirchhoff's rules, we've got series versus parallel, grounding, electrical safety devices is one of the ones that I think a lot of you guys are freaking out about. So yeah, it hasn't got any of the matter stuff, unfortunately, and it hasn't got pretty much any of the thermodynamics, but we've got a little bit of stuff here. So if you do want to go back, this is a good place to go for revision stuff. So you can easily get to that by just going to my thing. You can also subscribe, like, I mean, you don't have to, like, but come on guys, I'm trying to get to 1 million subscribers and I'm almost there. Maybe, okay, I'm getting there. Like, let's get to at least 100. But not really, I don't care. It doesn't bother me because I just put out shit. But the point is that you guys can you can use this to your advantage if you want to. If you're in my general maths class, by the way, hey, guess what? There's also general maths. Term 3, there is also a lot of term 3 stuff, but obviously, so afterwards, if you guys want to start to get a bit of a head start, guess what? You guys can start looking at term 3 stuff and be like, hey, cool, I'm going to get a head start. But we don't do that now. Focus on the exam now. Last little thing that I was going to show you guys would be, you guys can use as revision at the moment, is Enrollo. Now, in Enrollo, you guys can access the thing here. Let's go here. In Enrollo, you guys can actually see, you guys have got access. You won't have access to all the things I've got access to because I've got special access, but here you will have all of the different types of the topics that we did. So if you were like, oh my God, Mr. Greer, you went through the standard model too quickly. Well, guess what? You can watch someone else do the standard model instead.
So to get an idea of what we mean by a model and why the
he talks
now
about
I've got a worked example here, which is looking at this idea of our fractional charges. So our baryons,
blah blah blah, cool. So you've got a good place that you can go to for more information, and I believe most people are on this by now. I don't think every question 12B. Let's have a look. Let's jump to question. I assume you mean 12B of the short answer, yeah? 12. I'm going to have to look at the whole question 12 though first. So that's going to have to give me a second though. Uranium 238 decays to thorium 234. Yep. So And an alpha particle is shown, yeah, because, you know, 238 subtracts 4 gets to 234. There we go. Beautiful. Great. Cool. Consider the following data. We've got uranium-238. We've got uranium-234. And this is U. This is atomic mass units. We've got 4, and then we've got 1 U is this. So 1 U is a very, very small mass. Write down the full decay of uranium-234. Calculate the energy released in part A. Oh, that's a good question. I like that. Let's do this. So how would I do this? I would do this like this. I'm going to go with blue. I'm going to go with this. I'm going to say that uranium 92-238 goes to thorium 92 234 plus an alpha particle with mass of 4 and a charge of +2. There's your decay. Now, next, now that's really worth 2 marks. That's pretty easy. Calculate the energy release, and if you wanted to do instead 4-2 helium, that's fine too. Either of those would be fine. Calculate the energy released by the decay equation. So let's figure this out. So we've got to look at this. What's the mass on the left? And what's the mass on the right? So we've got, let me just scroll up a little bit. Just watch out though, the words are going to come with it. So we've got the mass on the left, we've got uranium. Just trust me here for a second. We've got, because I'm trying to do this normally. Yeah. So the mass on the left, what have we got? We've got uranium-2, we've already got a mass here. So let's just write down this mass. Our mass that we've got is 238.0508. The mass on the right is 200, because we've got thorium and alpha particle, we've got 234.04. 0426, and this is U, by the way, which is U, plus 4.0026 U. So, and then let's, there's a question here. Can you use the same amount? Okay, no, I can go through that, but let me finish this question first. So we've done this. So therefore, we now know that this is 238.0508 U, whereas this becomes a total of 238.04, and then we've got 26 plus 26, so that's going to be 52 U. So these are our two masses. So the difference is going to be, I'm going to get my calculator out, 238.0508 minus 238.0452. We have a difference of 0.0056 U, which is equal to, and if I take that number, multiply it by the mass, which is this tiny, tiny amount, times 1.6605 e to the negative 27, 1.6605 e to the negative 27 That gives us a mass difference of 9.2988 times 10 to the negative 30 kilograms. Beautiful. And you'd think, right, after all this effort that we'd be done, but unfortunately we're not done. But you can now see why this would be worth 5 marks, right? Because it's a difficult question. So now we just need to go E equals MC squared equals 9.2988 times 10 to the negative 30 times 3 times 10 to the power of 8 squared equals times, open brackets, 3 times 10 to the power of 8 squared. 8.369 times 10 to the power of negative 13 joules. If I divide that by 1.6 times 10 to the negative 19, that will give me 5230575. And that's how many electron 5230575 5230575 electron volts. That's what I calculated. Now, time to see if I made a complete mistake here, which is very likely. It is very possible that I made a complete mistake here. I'm just going to write this number down just so I can compare it. 5230575, 5230575, 5230575. I'm going to clear this. I'm going to open up the answers. The answers which I downloaded, answer booklets. Suggested solutions. 12B, right? 12B is 52306 and times, and it's times, so I got the correct answer. I'm happy. So what was so I'm happy about that. So let me see if I can, yeah, okay, look at that, I got it back. So the problem is now I've got to change back to here. So, oh look, it worked. Okay, that's pretty cool. So what was the difficult parts about this question? To do this question, you need to do a couple of steps. The first step you need to do is you need to calculate the mass on the left. You need to calculate the mass on the, you need to calculate the mass on the left, and then you need to calculate the mass on the right. So once you've got those two masses, your next step is to calculate the difference, and then convert that difference into kilograms. And once you've got that kilogram answer, you can calculate the energy. And then once you've got that energy, you can convert that into electron volts by just dividing by 1.6 times 10 to the negative 19. If you got this, if you got to the green part, then that's pretty good. If you go all the way to the blue part, then that's all right. Okay, let's now go with, firstly, before I move on, does that help, Elaine? Did that help you understand that? Is that good? Do you want me to go back over anything else with that question? Or are we all cool? Yep, good. I'm glad that you got that now. So I'm going to trash this. So then the next thing that says, sir, can you explain the standard model? Bosons, fermions, quarks, hadrons, mesons, baryons. Yeah, no, I'll give you a quick I'll go quickly over all of it again if you want. But again, it's one of those ones that you probably be better suited to go back over the notes, maybe even to rewatch the video that I put up. Did I put a video? Were we in lockdown for that? No, we weren't. Sorry. So you can't watch a video because the video doesn't exist. But I can go through it quickly with you guys. So let's open up a whiteboard. Let's clear all this RUD and we'll talk about them. So the standard model. So the standard model is the standard model is essentially a way that we can understand the universe. Now, the standard model has some pieces that go into it, and then it has some pieces that go into it, but then it also has some pieces that can come out of it. So let's start with the standard model. We'll break it down into two halves. Okay, one half we're going to call these the bosons. And bosons always lead with force. And then on the left, we've got our fermions. And they link with matter. So the bosons, we've got 4 bosons that we need to worry about. We've got a gluon. We've got a photon. We've got a W boson. We've got a Z boson. We've got a Higgs boson. Now, what's what, sir? You can't say what's that. So each of these are bosons, and they all agree with a different force. Gluon is the strong force. Photon is the electromagnetic force. W and Z bosons are all attached to the weak force. And the Higgs boson isn't attached to a force. It's actually attached to the idea of mass. And you might say, but sir, isn't that gravity? It's like, no, it's not gravity. It is mass. It's a little bit similar, but a little bit different. So those are our bosons. And now I kept saying to you guys, in theory, there is a graviton. But it's never been discovered. So therefore, we can't actually put that on. Because it's never been seen, it hasn't been discovered, we can't add it to our list. That's why I've done it in these weird dots. I wanted to do it in gray because then I could be like, yeah, but apparently I don't get to choose gray, so yeah. Okay, so that's the bosons. Now, next we move on to the fermions, which is all to do with matter. And there are 2 types of fermions. Those are called quarks. And we've also got leptons. In the quarks, there are 6 types of quark. We're up, top, and charm. You also have bottom, down, bottom, and strange. And I'm pretty sure, but I may have got these 2 confused, but you guys can, that these have plus 2/3 charge. I think the charm is the plus 2/3, but I might be wrong. Whereas the other ones have all got minus 1/3 charge. And as we go from left to right, it gets heavier. You don't need to know too much. You don't need to know the specifics, but that's that. So they're the quarks. But then you've also got leptons. Now, leptons are their own particles. These guys are very light in comparison. There are 3 leptons. They are the electron, the muon, and the tau particle. And for each of those, we've got a neutrino. We've got a neutrino, and we've got an electron neutrino. We've got a muon neutrino. We've got a tau neutrino. What's neutrinos, sir? Well, neutrinos are leptons. They just have, so these all have -1 charge. These all have 0 charge. So a neutrino has 0 charge and almost 0 mass. So therefore, they don't really interact with anything. So a neutrino is like just has, you know, very little charge, very little mass. Pretty much that's it. So what's the point of it then? Well, because what it can do is it can balance out the energy. So in beta decay, this is starting to go off topic. So in beta decay, you get a proton, a neutron, sorry, a neutron comes a proton the other way around. A neutron can become a proton, and you will release an electron. But here's the problem, right? If you release an electron, you need to have something to, if you release an electron this way, you need to have something released from this way to balance out the energy. So we need to release something to balance out the energy. So what do we release? We release a neutrino, specifically an antineutrino. And the reason we release that antineutrino is to make sure that the energy is balanced, not just the charge. But that's a bit off topic. This is beta minus decay. So that's the standard model. So I'm going to pop open chat again. I'm going to move chat to the other side now so I can. So then what happens if you take these quarks? If you take if you combine quarks, you get a combined quarks gives you a hadron. And there are 2 types of hadrons. There are mesons, which are 2 quarks, and baryons, which are 3 quarks. So what we're going to do is we're going to make a meson. And let me show you how to make a meson. I want you, we're going to make a meson. I'm going to let you make your own meson. So Noah, can you pick something from this top row and something from this bottom row? It can be any 2 things you want. Up and strange. So if you took an up quark, that has a plus 2/3 charge. Now if you take an anti-strange, what would an anti-strange be? It would be like a normal. That's going to be a negative 1/3, a positive 1/3, sorry, because an antiparticle is the opposite. It's going to have the opposite charge. So if you combine those together, you will have a total charge of +1. A meson always has a quark and an antiquark. And that's what a meson is. Now with the baryons, there's only 2 stable baryons, and those are a neutron and a proton. So what does a neutron have? Well, a neutron has two downs and one up. What does that look like? Well, that means we've got a negative 1/3 plus a negative 1/3 plus 2/3, which means the overall charge is 0. So that's why you have a baryon. It's a baryon is set together. If you take multiple baryons and put them together, so you can now start to get a bit of a hierarchy, right? Watch. If you take quarks, you can get a hadron or baryon. We'll go with baryon. If you take a bunch of baryons, you can actually make a nuclei of an atom. What do I mean? So let's do the exact. If you take a quark, so you've got an up quark. If you take two ups and a down, you have a proton. If you take a proton, you can get a helium nuclei. And then if you shove some electrons on there, you've just got helium. So ladies and gentlemen, so that is the standard model. If you got any, like, that's everything that we talked about in that whole lesson pretty much. Is there anything that, like, you want me to sort of touch on in more detail? So cool, good, I'm glad. I'm going to save this, but what I'm also going to do is, because I really want to know this, I want to know what the name of this meson that you made up. So you made this meson up in an anti-strange. I'm going to look up what the name of that is. What would be the name of an up quark and an anti-strange? Up and anti-strange. List of mesons. Let's see if I can find it. I want to know what it's called. Control F. Up and let's see if I can find it. I want to know what it's called just because it'll have its own weird one. Let's see. Okay. I wonder. Oh man, I can't easily find it, unfortunately, I don't think. Yeah, I thought I could just I thought there would be a lookup table. I could just easily find it, but it looks like we can't. Name. No, can't find it, but I thought I could. But I'm sure it's somewhere in this table here. But that would involve me understanding what, or maybe it's this table here. But I would need to understand what this table, how this table works, because I don't fully understand how this table works. It's interesting. I don't know what unflavored means. Like what? We're looking for an up and an anti-strange. It doesn't, like, yeah. Obviously, yeah. Yeah, no, there's no like combinations. Is this gonna work? Ooh. Here it is. Look. It's here. It's a kaon. We found it, a kaon, because a kaon has an up and an anti-strange. You created a kaon, and this is the anti-strange. It's a K plus, kaon plus. There you go. I learned something. There you go. Kaon plus. What is a kaon plus? They're mesons. These are just mesons. A kaon is a meson. A kaon, also known as a k-meson, a group of 4 mesons is sweet for their quantum number, blah, blah, blah. They are called called strange quarks. It's the bound state of a strange quark or an anti-quark and an up or a down quark. There you go. No, they're not going to be on the exam. Well, yes and no. What do you mean by yes and no? What I mean is this. So all you need to understand there is that you created a meson. The meson that you created was an up quark and an anti-strange quark. It has 2 quarks, 1 normal, 1 strange, specifically anti-strange. Okay, what I thought I would do as a bit of an extension is like, hey, I wonder if this has a name. And yes, it does have a name. The name of this is called a kaon. Okay, but I could also say, like, for example, there's also one called a pion. A pion is when you take an up quark, so plus 2/3, and you also take a anti-down, which means it's going to be opposite of a down. So the opposite of a down is plus 1/3. And that creates a +1 charge. And that's known as a pion. So a pion looks like that. So you just found a different one. Now, the thing that have freaked people out is like, do I have to memorize pions and kaons and zeons? No. You just have to know that they're different types of meson. That's all I wanted to do. All I thought would be interesting is like, let's find out what the name of it is. So we found out that the name of it happens to be called a kaon. Yeah, I get it. Good. So don't stress about it. I'm just doing this. I'm not doing this to be like, oh man, like, you know, I'm just doing this out of interest. I was like, well, if I'm going to be, if you figured it out, cool. I wonder what it's called. So you found, what's it called? Up in an anti-strange. So you found a K plus. So it's called a K plus. You can also have a kaon 0, which is when you have a down and an anti-strange, or a kaon. You can have a K short, which is, I don't know, it says this. That's a bit weird. Okay, we're going to ignore this. This is a bit too complicated. But these 4 make sense to me. But you don't need to know them. You just need to know that these are mesons because they have 2 quarks. Beautiful. At this point, let's have a look at question 10, the multiple choice. The reason I'm ignoring your question, well, sort of ignoring your question. First thing, no, I am sort of ignoring your decay question because of two reasons. One, because I thought I've already answered 2 of your questions, but 2, one of your big questions. But also, I have uploaded a YouTube video about decays. So you've got about beta decay. As for the alpha and the alpha decay and the gamma decay has no change in mass. So there's not really much that you need to worry about there. And as for the alpha decay, at least there's no weird alpha decay, so it shouldn't be too difficult. Let's have a look at question 10. You say question 10 of the multiple choice, right? Unless I was mistaken, you said something else. Question 10 of the multiple choice. Wait. Okay, so the stable isotope boron is bombarded with neutrons and forms lithium-7 by emitting alpha particles, as shown below. Okay, so no, I don't think you need to know what these 2 things are. I actually don't fully know what these things are anyway, but I can tell you, obviously, this is fission. We're taking a heavy element, we're breaking it up into smaller elements. So that's fission. I think this is like, I don't really know what artificial transmutation is. I believe what it would, transmutation means to change. If anything, this would be artificial transmutation because you're hitting it, you're changing it artificially. This would not occur in nature, but I'm not too sure. Let's just have a quick look. The conversion of element to another fundamental. Okay, so artificial transmutations when you hit things with particles that are not. No, I don't know. I would have to look this up. I'd have to go into a bit more detail, but I've never heard of it before. I think it's one of those ones. It's like, again, this exam. This was not. I didn't make this exam. Someone else did. So yeah, is there a natural transmutation? So artificial transmutation is when you hit something with a particle that's not a neutron. So you're hitting it with an alpha particle or gamma particle or a beta particle or something. What about natural transmutation? Does that tell us what that is? Natural spontaneous transmutation is unstable rate of these elements will be formed into stable nuclear elements over time. Oh, okay. So natural transmutation is just, okay. So the answer says C. Huh. But it's also A. That's a bit weird. Sorry, I am listening. Well, we're almost done, by the way, with time-wise. And so this will be the last question I get to sort of talk about. It says the conversion of an element into another element of a body with fundamental particles is artificial transmutation. So because you are bombarding the boron with, I think what they're trying to suggest here is, am I sharing? You're sharing a screen. Which screen am I sharing? Am I sharing the screen? I am sharing the screen. So because you are bombarding it with a neutron, it says, oh, you're hitting this with a neutron, then that must mean that this is artificial. This is human-made bombarding. Human-made change. That's what artificial means. Whereas natural, that's like decay. So it's like the natural decay. My problem is that, oh, I know why this isn't fission. Do you know why it's not fission? There are no neutrons coming out. There are no neutrons coming out. So this doesn't count as fission. Because if you look, you're adding the neutron into this equation. So what I'm doing here, Elaine, Elaine, is it you that asked the question? Yeah. What I'm doing here, Elaine, is I'm answering the question. I'm learning stuff and then answering this question as we go. But I guess the moral of the story is, one, this is not going to be on the exam. Is it still worth learning? Yes, I think so. So what have we got here? We've got artificial transmutation, which is when you hit something with a particle. You got natural transmutation, that's like decay. Fusion is where you take two particles and you combine them together. And fission is when you do this, but you get a neutron out. So then if you think about it, right, if you take uranium 238, and you hit that with a neutron, right? That will form, let's say that forms, I think it's like, I can't remember what it forms, but I think it forms like bismuth something, and plus 3 neutrons. If you were to look at that, you put 1 neutron in, you got 3 neutrons out, you're not adding neutrons. So I think that's what they're trying to do. Again, you do not need to learn this. I just wanted to show you the correct answer and how to work it out. What I will do is in the future refer to decay as natural transmutation, and artificial transmutation is like changing something. But you know, you don't need to learn this for this question. You don't need to learn this for the exam. But it's still worth to talking about. Hope that helps. I know that it's annoying when you get a question like, I don't know what this word is. It's like, well, I didn't cover it, but you know, it doesn't matter too much. That is the end of this lesson.